empecemos. Vamos a ver. Okay, I think we are live. So, hello everyone, and welcome back to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. So on this day, we have Jose Zurita as a speaker, who is a junior group leader at IFIC in Valencia. Jose carried out his PhD in Buenos Aires and then had postdoc positions in Zurich, Mainz, and Karlsruhe. For this webinar, which is the 136th one of our series, Jose will give us an overview of searches for long-lived particles, and we are very happy to have him as a speaker today. Now, before we begin, let me remind everyone that you can be part of the discussion, writing questions and comments via the YouTube live chat system, and the questions will be passed over to Jose at the end. Okay, so we're all yours.
Okay, thank you very much for the nice introduction. So let me share my screen. I have way too many windows open. I don't see my keynote. Where it is? Please. Odd enough. I had it last time. You see, this is why one should.
One should have that.
Give me 1 second. We're having technical difficulties.
There's a problem for asking you not to share the slide at the beginning.
Yes, this was my strong motivation. So let me see if I can get this back on track. Okay, perfect. I think it's there. I don't know if everybody can see it, and there should be no green bar whatsoever.
Yes,
right?
Everything good.
Good, perfect. So I want to thank Joel not only for the nice invitation, but also to be in this series of webinars. I did my PhD in Latin America, so I'm very well aware of this fact that we get the meal, but we get it cold. So this is why I will try to contribute to this effort to bring you an overview of what is hot right now in the realm of long-lived particles, or in a more Hollywoodesque setup, the lifetime frontier. So this is a topic that touches upon on many different aspects of high-energy physics. So I won't be able to make justice to many of these branches or research lines. But of course, you can just email me if you want to have more reference to the literature, or I mean, at least I can try to guide you if you want to know more about a particular topic, or of course, if you want to just give me feedback, comments, or whatever, I'm open. And probably in one of the many papers I will cite that I work, you can just go there and find my email address. Okay, so I'm a collider physicist. What I want to do, I want to disprove the Standard Model. It's a beautiful theory. It works fantastically well, but it has a bunch of issues and problems and things that make us slightly uncomfortable and don't let us calmly sleep at night. Like 10, 15 years ago, people said, okay, these new physics problems are going to be solved, most of them by physical relativity scale. The flagship was the hierarchy problem. And we said, there's no way this can evade the LHC. Now, the hard truth is that there's nothing really significant coming out of the LHC data. And one needs to take a small break, breathe deep, and say, okay, what's going on? What are the possible logical explanations for this apparent lack of this new physics? Well, this would take us hours of therapy, but we need to admit that maybe the new physics doesn't like collider people. Maybe we need to directly look for actions pointing at the sun, or go to something like Dune or Hyper-K, and neutrinos will reveal it to us without any inference from colliders. The second option is, well, maybe we screwed up at some point in the calculation, the estimation of where the effect should be. Maybe it wasn't at the TeV. Maybe it was at 10 TeV. Maybe it was at 100 TeV. So maybe we need more energy. Maybe we need to do these things more precise and try to find deviations, for instance, what people at Bell would do. Or the third option, which is the one I'm going to focus mostly on today, is that the new physics is there. It's not that it hates us, but it quite of like doesn't like us. It's playing hard to get. And this is when it works in stealth mode. So it's there, but there are some limitations of the LHC mostly that doesn't allow us to directly see it as we would have expected. And this can be as low as something like, let's say, 100 GB to 1 TB. There could be still plenty of new physics there that just isn't in the best scheme form for us to grasp from the data. So these difficulties also bring us together a bunch of opportunities, a very fertile territory to look for new physics, both from a theoretical and an experimental perspective. So what I will try to do today, my plan is to first try to convince you that LLPs are something that are sound and it's not a sort of last-minute resource that theories are doing because we are not finding the new physics. Of course, you can think we're just making up new particles that we know don't exist, and you can write down some popular article in The Guardian, but this is not what I want to do. I believe in the particles I'm postulating. Then I'm going to briefly touch upon, I'm not an experimentalist, but if you follow the archive, you might have seen that there are a lot of dedicated detectors for LLPs that are coming more or less once a month. You should have a new one. And then I will try to tell you what is this idea about and why there are so many. And then checking this webinar and the height and the size of the keywords that are in the web page, I realized that there's a very strong preference for dark matter. So I'm going to focus my 3 big examples of LLPs on aspects of dark sectors. I'm going to talk about WIMP dark matter. I'm going to talk about film dark matter. So one of the nicest is one of the best world-known experts on film dark matter. So I won't need to explain much, and he can answer questions on that aspect. And I'm also going to talk about a sort of fairly novel topic, or maybe it's not so novel, but it had received some extra boost in the past, which is a topic on dark showers that have to do with having strongly interacting dark sectors. So that's dark sectors where the interactions look more or less like QCD, and this is our guide for that. Okay, so what about long-lived particles, the motivation and the challenge? This is what I want to introduce them. So for the purpose of this talk, I'm going to define a long-lived particle as a new physics state that leaves a macroscopic distance such as I see it in the detector. It's a very vague definition. And it's important that I say BSM, new physics, because if you look at the diagram on the left that I am hopefully pointing with my pointer and you're seeing, in this diagram you can see the lifetime in meters on the y-axis versus the mass of the standard model states, not only fundamental but also composite particles like the B mesons, the kaons, the pions, etc. And you see that this, in the standard model alone, expands a very large range of lifetimes. Okay, and there are very good reasons for that. There are theoretical mechanisms that make these particles long-lived. So, but we want to look for particles that are not the ones that we know of. Now, this is one option. Say, okay, theory can give you these particles. And you can say, I want to look into theories that solve this kind of electrobaryogenesis or dark matter or other problems that are in the standard model. There are very concrete models where LLPs exist. Or you can take an approach that is more from the experimental perspective, that is, okay, I need to look for these particles. There are a lot of very interesting signatures because the LHC was designed for collisions coming from here, the interaction point, and particles being produced that don't live too much, particles that are what we call prompt. Here, in contrast, depending on how long the particle lives and which kind of particle it is, what is the standard model quantum numbers, what it decays to, you will have this very nice sort of pixel diagram of the signatures. And here, not only out-of-time decays are not pictured, but also the full breadth of dark showers is not present in there, because when this diagram was done back in 2017, dark showers was just emerging as a sort of subfield within long-lived particles. Okay, so essentially, if you want to look for theory motivations and try to loop over different models and why they will give you LLP signals, I recommend you this publication. And if you prefer the signature approach, I would recommend you this other one, In both cases, you can find more information about these things. So what I want to do now is take stock and say, if in the standard model, there are long-lived particles, I can try to scrutinize some of them and see why they are long-lived, and then try to see if those mechanisms exist in BSM. I'm not trying to make the claim that BSM should be like the standard model. All I'm saying is that the mechanisms that make particles being long-lived can apply to other BSM theories. And I will try to also tell you in each of these cases what is the LHC limitation that doesn't allow us to be fully sensitive to these scenarios. So if I just ask people, okay, tell me what a particle in standard model that lives long enough, I think that people will answer 80% the muon. Okay, so the muon lives long enough because the W decays of shell, and then the rate of the W mass, which is the one that says the energy of the full thing, or if you want the inverse of the Fermi constant, however you want to see it, makes the width very small. Now, if you do this calculation in the standard model, but you assume that this I could try to BSM, so I could change right now electron, muon, and the coupling for some BSM parameters, you will see that what you have is an electron over muon mass to the fourth power. That is what gives you this very small width or very large lifetime. And here I can just put some numbers in concrete theories where you will get something like a centimeter. Now, other thing that can happen, and what happens to us, luckily, in the way that the neutron decays to the proton and not vice versa, is if the spectrum is very compressed. Okay, and what makes this lifetime here larger is the fact that the mass difference of the neutron and the proton divided by either the proton or the neutron mass is a very small number, and to the fourth power is an even smaller number. So the width is small, the lifetime is large. And this is something that can happen, for instance, if you look at supersymmetry or even minimal models of dark matter will give rise to compressed spectra for theoretical reasons that I won't describe here, but this is a very normal situation. Now, the other thing that could have happened in the standard model, it did not happen quite in the example I'm going to give, is that you could have a very small coupling for whatever reason. This could be a coupling that must be small because of some thinner reasons. Okay, neutrino mass is very small, and then the Yukawa there is small, and then I can think why this is small or not, but I need to live with the fact that it's small. Or it could happen that, for instance, there's some symmetry that got broken, and this generated this sort of soft breaking of the symmetry, generated a coupling that if the symmetry is restored would go to zero, so the coupling is sort of fated to be small. And for instance, here the example I like is to think of a set decay into neutrinos, but if the coupling is small enough, something of 10 to the minus 6, then the square is 10 to the minus 12, and you can easily get something like a centimeter. This is not the case in the standard model, but if I take the standard model and change the axial and vector couplings of the set, I can probably make the set to be long-lived. Okay? We just don't happen to have it. And the point is that each of these mechanisms, either having a hierarchy in masses or a compressed spectra or a very small coupling, is tied to LHC limitations. If you have a very large energy scale, you're not directly producing this particle. It's outside of your reach, and then you need to deal with indirect effects. You are not able to produce it, as we say, on shell. Now, if the spectrum is compressed, there's no problem with the spectrum. Well, the problem with the spectrum compressed is that the decay products of this process tend to have very small energy, and moreover, very small transfer momentum. So the ruler to have the quality of an object, an electron, a muon, etc., the collider, is tied to its transfer momentum. And if you don't have enough energy, you don't have enough transfer momentum, and then you go below the reconstruction thresholds. This is quite a challenge, and people have become quite inventive on trying to overcome it. And then the last one is sort of obvious. If you have a very small coupling and you're using it somewhere in your production, then your rate is very low. And that's it. And it's something you have to deal with if this coupling is doomed to be small, or try to test your model in another way. So I just want to point out, because when I started focusing more on LLPs, people told me, yeah, you are doing probably like displaced vertices, right? And the richness of LLPs go way beyond that. Sure, in this diagram there are displaced leptons, displaced vertices, displaced jets, but also stuff like heavy stable charge particles, disappearing tracks, or these out-of-time decays and dark showers that are not just displaced vertices. A displaced tau, displaced jet, displaced muon, but something that is slightly more complex, which is more challenging, but it's also a lot of fun when you work on it. So what are the hot topics, the discussion, the challenges, the things that are happening sort of the LLP world? So the problem, and I already stated it, none of the general purpose detectors, I'm thinking of ATLAS and CMS mostly, were built with long-lived particles in mind. They were built to try to catch particles that are prompt, originate from the interaction point. So issue number one, huge issue, triggers. In a LHC, you get a bunch of protons, something like this, in 25, 40 protons, whatever, they clump together, and then there's another bunch coming right behind you, they have to collide. There's no way the information that comes out of this collision can be recorded. There's no humanly possible way to record it. So what the general purpose detectors do, they say, okay, we're going to look for interesting effects. For instance, I'm looking for the matter, if there's a lot of missing energy, I am going to save the event. But if it's too little, I'm not interested. And sometimes the triggers work for the model with LLPs that you have in mind, and sometimes the triggers are highly suboptimal for what you are trying to achieve. And this is why the LLP working group wrote this. I'm going to tell about the LLP working group in 2 or 3 slides. Wrote this document, essentially trying to exploit and explore trigger opportunities that could be deployed in the next LHC run aiming at LLPs. Now, you are dealing with objects that you are not expecting to deal with, so you need to change your analysis strategies. This is something that goes pretty much within the collaborations. It's not so much something that affects us theories, but certainly there are a lot of creativity and inventive and thinking out of the box to deal with this stuff, because you wanted a muon that had a track that points to the primary vertex. But what if you have something that decay into the muon, but after the tracker? So you only have information from the calorimeters or from the muon chambers. Okay, so you lose an important component with what you call a muon. It's a different object, period. That's the way to, even though it's a muon that got displaced, from the detector perspective, it's a different object. Now, something that is a very hot topic I would see in almost any LHC search is the topic of reinterpretation. An LHC search is done with a concrete model in mind, and they normally present limits in that model, and if you're lucky enough, they present limits in some model-independent way, or proto-model independent, or pseudo-model independent way. Now, what do you want to have? You want to have the flexibility that you take one LHC search and you apply it to a model that wasn't the one that was designed the search for, and you still get results. And this is certainly quite complicated for several reasons I already pointed out. And there's a lot of effort ongoing in the reinterpretation forum that mostly was dealing with prompt signals, but now is moving to tackle the issues with LLPs. Now, there's this full new chapter that I hope to have enough time to discuss, which is dark showers. So this is a sort of new kind of signature that wasn't systematically explored before in these searches. And there's a bunch of new experiments that are placed slightly outside of the LHC to catch long-lived particles with that goal, that not only are being proposed, but they are also being approved. So if you say, okay, I don't care about these things, well, but they're becoming like official experiments with the same status as ATLAS, CMS, LHCb, or all the others. So just a very quick propaganda slide. There are 2 important bodies that I want to tell you about. One is the LLP working group. The idea of the LLP working group is try to establish a dialogue between the experimental collaborations, the theory community, provide recommendations, help to communicate things, for instance, how to reinterpret a given search, discuss possible new searches, etc. There are conveners from the different experiments on the theory community, and as you can see, Giovanna Cotin from Chile, who's based in Chile, is one of the theory conveners, together with me and Nishita Desai. And of course, if you're interested, please click in the webpage. The link hopefully should be clickable. If not, you can just type in a browser. And we have a mailing list where we update on the projects that we are having and so on. And the second body is the long-lived particle community that is operating since 2015, organizing workshops where people come, discuss stuff. So there was a white paper that is the one that have this signature-based approach. There's a lot of things we have done there. There's the link, and this has been also the incubator and the source of many initiatives, many collaborations I wrote, more dedicated workshops, some other initiatives like the LLP recasting repository I'm going to discuss in a few slides. They all came, grew up, flourished, thrived under the LLP community umbrella. And maybe next year we will move from a 2 times a year workshop to a yearly workshop according to a poll that is being processed right now. But nonetheless, I hope to see many of you there. So after this advertisement is done, let me tell you slightly about the dedicated detectors. I'm more or less on 20 minutes mark, so I'll try to rush up. So here I have one example, which is MATHUSLA. MATHUSLA is a very huge detector of something like 100 meters called 100 meters times 25 high. So think of a football stadium or an IKEA shop that is trying to catch the particles that come from here that could be either on CMS. The idea is incredibly simple. LHC can produce a lot of particles because it has a very large energy range up to 14 TeV. It's one of our best sources of long-lived particles. And the only thing we need to do if these particles are neutral and get out of the detector and decay afterwards, we just need to put the detector somewhere to catch them. How, which technology, how large, where, it depends on what your physics case is. But this is the idea about on these many detectors. Now, why to build them? A general purpose detector is supposed to be robust. It's supposed to be, with quotation marks, model independent, try to catch as many new physics signatures as possible. And it's composed of many systems, tracker, calorimeters, muon chambers. So you have a lot of handles on the particles that you see. But it wasn't designed for LLPs. Certainly, there are many difficulties. Now, on the contrary, a smaller detector, which also I didn't put in the slide, but is way cheaper than the LHC, than ATLAS or CMS or LHCb, can target a particular case if you put it in some particular place with the goal of reducing or even skimming the backgrounds. You don't need trigger, and if you say, I want to look for lonely particles that decay into photons, then you do a detector that is beautiful on photons, and that's it. Now, also something that is important is this particle that you produce and is long-lived could be 1 GeV, could be 1 TeV. If it's too light, it will have very small PT, so it will mostly go in the forward direction. And if it's much heavier, it will go mostly in the transfer direction. So you need to put detectors in both sides. And a very nice summary was done by my colleague Matthew Citron from CMS, where what he did here is he classified the detectors by distance to the interaction point that go from meters to hundreds of meters, and the kind of mass range that is targeting, either MEV, GeV, or TeV. And then whether in blue, you look directly for the long-lived particle, or in red, you look at the decay products of the long-lived particle. And you see there are many names, and some of these names are actually official detectors of the LHC, and some other names are essentially in a very advanced process of trying to become a detector. Okay, an official experiment. Good. So what are these detectors good for? These detectors are good for light, standard model neutral new physics, in a way that, because if you want to have light new physics, or like the GeV scale, it should have a very LEP, Tevatron, searches for EDMs, flavor factories, etc. And a very simple mechanism to make those constraints be mostly relevant is to say, I have a portal, I have a new physics that is over here in the Lagrange, and I have a standard model on the other side, and I have a term that connects new physics with the standard model. And depending on whether this new particle is a scalar, vector, fermion, or pseudoscalar, you get exotic Higgs decays, dark photons that can be a dark matter mediator, a heavy neutral lepton or a stellar neutrino, so this is connected with neutrino masses, or an axion-like particle that is obviously connected with a strong CP problem. And if you look at these different models, what these different detectors will do is produce very busy plots like that, where you have many lines. Some of the lines are Bingham experiments. Some of the lines could be, for instance, over here, BBN, so comes from astrophysics, like BBN or supernovas. Here you have like CHARM, which I understand is a Bindam experiment, or you can have LHC experiment or these proposed experiments like CODEX-B or MATHUSLA, and then you can do this for, depending on the decay product, if these are the photons that decay visibly or decay invisibly, or these are heavy neutral leptons. You have your own very busy plots where many different experiments from also different communities, particle, astroparticle, etc., coming together. And if you look at these plots, these extra lines that are not shadowed because they are proposals, they tend to cover more parameter space, which is what morally justifies the design and the deployment of these detectors. Good. Now, as I try to tell you, LLPs are almost everywhere, and there are many things I'm not going to touch upon. I leave you here a probably incomplete and unupdated list, and you can probably add your favorite topic on that, and maybe you will add a paper at some point. I'm going to focus, as I said before, on dark matter. Okay, good. So I'm doing more or less 25 minutes mark. Okay, I think I'm doing more or less fine. So I'm going to start with the compressed WIMPs, which essentially manifest most of the disappearing tracks. And I'm going to tell you about these two Fino papers that I wrote, and also one Atlas paper that we strongly exploit. So this is a lot of theoretical blah blah, but the idea is fairly simple. If you want to have dark matter and you want to make it in a minimal way, the only standard model charge that dark matter can have is SU2 left. It cannot have color because it will destroy stuff like structure formation, will be totally different. And it cannot have electric charge because we wouldn't be calling it dark. It's sort of obvious. So what people do is they take different multiplets, like triplets or doublets, and then they play with the spins, like could be a vector or a fermion, and they try to get dark matter out of this. This is normally going under the paradigm of minimal dark matter. And when you have these electroweak multiplets, what happens is that you have one of the components you want to have the quantum number such as this electrically neutral, and that's your dark matter candidate. But if you have more than a singlet, if you have doublet, triplet, fourplet, etc., you start having electrically charged states. And those electrically charged states are slightly heavier than the neutral one, but not that much. Something of the order of 100 MeV or so, which is already enough to make them long-lived. And this is something which is very robust. It's a one-loop electroweak correction that goes in there. And it's pretty much independent of the mass. If your dark matter is sort of above 100 to 100 JeV, there's almost no effect on the dark matter mass itself. And this mass splitting is essentially a function of the spin and the SU2 charge of your multiplet. So what people was doing is looking at this charged particle being produced, is long-lived, and then it decays into a neutral one, and normally a pion, because this is what the mass difference gives you. But the pion is something like, let's say it's 100 MeV, and you have stuff that could be 1 TeV. So you have a particle that is 1 TeV plus 100 MeV that decays into a particle that is 1 TeV, and then there's like 100 MeV for the pion. So the pion is totally lost. Nobody sees the pion, although it could be seen in some other environments. And what you have is something that looks like a charge track that all of a sudden, boom, disappears. And then what continues is the dark matter that is invisible to the detector. This is why it's called disappearing track. So what is the interrelevant variable here is the PT of this charge guy, which is what we are plotting here for the different models. And our point here is that the red and black lines that were the ones that would directly map into Higgsian Wien dark matter in supersymmetry are the ones that Atlas was using as a benchmark. But if you take two other examples, that would be like a scalar doublet or a vector triplet, the PT distribution is totally different. Then you cannot directly interpret the results as they are from Atlas paper because they are based on these two models. They actually present one plot for each model, but kinematic-wise, they are essentially the same. And this is because what is mattering here most is the spin rather than the actual quantum number where it's a doublet of a triplet. So then Atlas produces this kind of information for a given mass and a given lifetime. It gives you an efficiency map. It tells you if you have a particle that you generated with a Monte Carlo parton level, how does it translate into a disappearing track itself? If you do that and you put that information, what you can try to do is try to reproduce the Atlas curve And then you can reapply those constraints to these two new models, the green and the orange were models that were not considered by Atlas, and by reinterpreting these results of these appearing tracks, we got the strongest constraints on this model up to date in some region of this lifetime. Okay, and here you have ticks. Ticks is where the missing energy searches value. So whatever is this sort of belly shape is new territory that we excluded by simply reinterpreting this. But then you can tell me, well, but that matter, these minimal models, I really care if I hit the thermal relic, like 1.1 TeV for Higgs. Can you do it? LHC cannot do it. But this can be done, for instance, future colliders, so both for Higgs and WINO. And these two upper plots are result from a paper that I wrote with Rodolfo Capdevila, Fede Meloni, and Rosa Simoniello on trying to look for disappearing tracks but at the muon collider, which is a total nightmare because the muons decay and the background is huge. It's huge. When people tell you lepton collider is clean, they are not thinking of a muon collider. They are thinking of an positron collider. And then after doing a lot of struggling with these backgrounds and designing a strategy to remove them, we actually are very, very competitive with the FCC-HH, which obviously we knew before we started the study that could do it. And of course, these are preliminary studies outside of the collaboration, so there's a lot of room for improvement, but the thermal target will come with future colliders. So LLP is also an important physics case for future colliders. And also the idea, the initiative that I wanted to showcase is that this reinterpretation of the Atlas disappearing track search went straight ahead to something that with some other colleagues was put forward, mostly by them, not by me, that this is LLP recasting repository, where the idea is that if someone takes one of these LLP papers and tries to make a reinterpretation, and you do some code that will do that, or even design a procedure, you just write a couple of pages, you can share your results because they can be useful for the community. And actually what we did for this other paper that I was showing you on disappearing tracks, here the entry over here that says new, I took the screenshot when we uploaded this, we uploaded the code and sample events that encapsulate our procedure in full. And of course, if you are looking at other searches, some of these efforts were put there. Of course, it's not mandatory to do that, but we believe it's a nice resource for those who want to reinterpret search in their own models. Okay, now I'm going to talk about a slightly other paper that is about feebly interacting massive particles of filmed dark matter. Now, I don't know how much you know about filmed dark matter, but probably should be asking Nicolas and not me, but nonetheless, let me try to explain this. So the normal freeze-out mechanism, what happens is that one is in equilibrium with the photons, with all particles in equilibrium, standard model goes to dark matter goes to standard model, boom, everything is working fine until the universe decides to do two things, expand and cool down. When it expands, yes, the standard model particles produce dark matter particles, but then these particles became far apart, and then they cannot find each other to decay to the standard model. So the decay from the dark sector to the standard model is blocked. When things cool down, and assuming that for simplicity argument, dark matter is heavier than the standard model particles, at some point the standard model particles don't have enough energy to produce the dark matter. Temperature is energy. So that's it, you stop the production. And this is how you get the black line. This is a very simplified picture, but I hope it works. Now, freezing has a slightly different approach. In freezing, you are never in thermal equilibrium. You have a very small coupling that prevents you to getting there. And what you do is sort of, your dark matter looks very much like when you put dust under the rug. Okay? You start with a certain number that could even be 0, and slowly you start accumulating it and aggregating it. Okay, until you get Boltzmann suppressed, the process cannot continue, and then you froze in at whatever value this have, and with a bit of luck, you froze in at there will be some parameters that will give you the right relic. So, what is relevant for colliders? For colliders, what is relevant is to think of a model. I should have put the Feynman diagram where you have a Yukawa-like structure, where you have a standard model particle that here I'm calling F in this notation. you have a new dark matter particle I'm calling S, a scalar, and then you have a standard model fermion. It's a very simple vertex. There are many constraints that you will put in there, but the idea is that this coupling, due to the freezing nature of needing to be out of equilibrium, needs to be small. Small coupling, LLPs. I mean, this is what at least should come out of the talk. So we move forward with that idea. And you see that you can get the lifetime as a function of the relevant parameters. And more interesting, in this very simple model of two new particles, you get an integral that goes from the reheating temperature to the temperature nowadays. So there's a certain sensitivity to reheating temperature. And if you reheat way too below the weak scale, then this would disprove essentially leptogenesis and baryogenesis in its more vanilla form. So what is the idea? There are many, many searches here that we reinterpreted in terms of lifetime and mass. And one of the strongest messages of this plot that I like a lot is that you cannot rely on one single long-lived particle search. They target different lifetimes. So if you follow the envelope, each of these searches is doing something. And also if you follow the envelope, the middle regime is the most challenging one. And there could be easily be something, look, if you say, the LHC has 14 TeV, but here I'm excluding something like not even 300, 280 or so, where I'm putting the pointer, and this sort of middle regime between having a very long-lived particle or a very prompt particle is certainly a blind spot of these searches. Now you can draw different curves in this plot that depend on the parameters, including the reheating temperature. And then you can take a look into the future. So extrapolate the searches to the high-lumi LHC under some wide or pseudo-reasonable assumptions. And you still see that you will not get much farther than 400 JeV or so. The dashed lines of extrapolation, the solids were the current one at the moment. They didn't move much because we were already mostly at the end of the run. But this means that you have a shot with the green one and with the red one to catch this other line that is where the reheating temperature becomes 160 JeV. So you can start making some cosmology with the long-lived particles and a collider. Now let me get into the world of dark showers. So in terms of dark showers, I'm not going to focus. So you have the work dark, I grant that to you, but I'm not going to focus on dark matter itself. I'm going to focus more on a dark sector. And the question that leads to dark showers is, okay, what if the dark sector where dark matter could live is not weakly interacting, but rather strongly interacting? And our guidance there is QCD. And this is something that goes back to 2006 under the name of Hidden Valley Models, this seminal paper by Matthew Strasser and Katrin Zurek. And what you need to do is very simple. You put new matter fields. We call it dark quartz QD, new gauge fields, dark gluons. You can couple both through the port as I defined before. And then say, okay, I have a certain number of colors. I have a certain number of flavors. At some scale, this should confine, because I'm really thinking of a QCD-like regime. Of course, depending on NF and NF dark and C dark, you will or will not have confinement. Okay, you will need to compute the beta function, etc. Like you do in QCD and say, oh, there's asymptotic freedom, there's confinement, fine. Now, from a pure phenomenological perspective, practical perspective, what should I care about? The dark core mass, the confinement scale, and the energy. And essentially, in this very broad picture of having strong interacting sectors, there are three regimes. One regime I want to focus is where the dark quarks are below the confinement scale, and the confinement scale is much smaller than the energy. This means that I can produce many particles, yes, because I have enough energy to produce many of these particles, and this dark quark sector is such that this will confine like it happens with everything below the bottom in the standard model. So there will be sort of dark pions, dark kaons, dark Bs, dark D mesons out there. Now, the other option that could happen is that your confinement scale is maybe too high. Maybe you make 2 or 3 of these particles at most, And then you are not looking anymore at the dark shower, you're looking at the resonance. And you can apply normal stuff. So this regime is interesting. These are dark bound states that you will form, but it's certainly not as striking as what I'm going to tell you about. And then the other option that I'm not going to tell you about, which is super interesting, but this probably deserves another separate seminar, is quirks, where this is like having the top. You have the confinement scale is below your quark state. So you have free quarks out there. Okay, they don't hadronize. They form a bound state that is very weakly bounded, and the phenomenology is super interesting. But again, it does not really belong to this talk. But if someone wants, I can point you to the literature in that topic. So, as I said before, dark showers, strongly interacting sector. I am going to take my lore from the standard model QCD. What do I know about QCD? I only need two properties here. When the energy goes to infinity, the couplings go to zero. Vice versa, if the coupling goes to zero, the energy goes to infinity. That is what we call asymptotic freedom. And when the coupling blows up when your energy approaches what is called the lambda QCD, the confinement scale. Now, the problem or difficulty or obstacle from a particle physics perspective is that most of the people that do new physical colliders is used to be able to compute for the Lagrangian parameters observables. And right now we cannot. We cannot compute the hadron masses or anything like that because the theory is strongly interacting and you need to use some non-perturbative methods as lattice. But what you can say, you can make some statements about the infrared perspective. So if you have, for instance, two flavors, yes, in QCD, you know that you get baryons that are the neutron and proton around 1 JeV, so 1000 MeV. You get vector resonances, rho omega, that are more or less a 700 something. Lambda QCD is of the order of 300 MeV. And below lambda QCD, you get the pions. Okay? So since the pions are the lowest lying hadronic states, this is what I'm going to think about. I'm going to think that my dark sector generates a lot of dark pions. Okay, in the standard model, look how funny this is. The charged pion lives almost 8 meters, and the neutral pion lives hundreds of millions of a meter. So millions of centimeters. It's quite striking that these two guys are mass degenerate in principle. Okay, then there's a small correction. Pi plus is heavier than pi zero. And this totally changes the lifetime of this particle. So, QCD at the Hadron Collider is very complex. It has many different ingredients. But what is interesting for us to know is that the parton shower, essentially, once you produced what is called your hard process, that is what you normally draw in your Feynman diagram, then what happens is there's an emission of gluons and quarks, and quarks mixed to gluons and so on. And this parton shower is perturbative. It's under control and can be computed. What cannot really be computed is hadronization, where you turn your quarks into hadrons or mesons. Good. So then, in view of that, your dark shower can be characterized in the following way. You have a production mechanism, that is going to be a Feynman diagram. You have the shower and hadronization part, and then you have the decay. And the real variable that you should care about is the product of the fine structure constant of the strong sector times the number of colors. If this is small, so like in QCD, you actually form jets, dark shells. Recall that this value is something like 0.3 in standard model QCD. If this number is large, okay, then you don't do dark shells. Your energy, instead of being focused in a couple of structures, it gets more split isotropically in the detector, and it gives rise to what is called soft and cluster energy patterns, or SUPs for short. Now, the other variable that I need to care about is my dark sector is such that my pions are long-lived or not. If my pions are not long-lived, you will have what is called semi-visible jets. If your pions are long-lived, then you will fall into the realm of emerging jets. So what you normally do, you take a production mechanism that you don't need to take, to be fair, because it's just a trick to have some signal at the LHC. And you say, okay, I can take a set prime, and this can give me rise to semi-visible jets, or I can take a T-channel model, that's also this other one that gives rise to emerging jets. Now, just to see how new this all is, there's only one Monte Carlo in the market, which is PTI-8, that can simulate their showers. Okay, and normally, if you try to go to any LHC process, you have a very large choice of Monte Carlos that can be at the general purpose, sort of like MATHGraph, or can be specifically targeting particular processes, something like axion. There's only one tool, which is also a limitation, but just tells you how new the subfield is. Okay, so for semi-visible jets, what happens is that you produce dark pions, but these dark pions don't live much. So they add to the missing energy component of the jet that normally you will have neutrinos. So what the search does at CMS is they essentially count how many stable particles you have in the jet, and they normalize by the total number of particles. This is the invisible fraction of the jet. So if you have no invisible fraction, you have a resonance. And if you have a full invisible fraction, this is like a dark matter search. And essentially what the semi-visible jets can do for you is, if you look at the plot on the right, is interpolate between the R equals 0 and the R equals 1 regime, where a dye-jet resonance or a normal contact interaction / missing energy search will win, but the red curve will win all in the middle. And this fraction is a number that will depend on exactly which dark sector you're putting in there. Now, there's only one CMS search that does a very simple selection. Then it follows the zeitgeist and takes 15 variables and boom, directly into the VDT and get the result. This is the very first experimental result for semi-visible jets of the LHC. And if you look at the archive date, this is December 2021. So again, very novel, very fertile, very young subfield. There's still room for you to jump in. Now, emerging jets, you do your dark mesons, normally your dark pions, but they are long-lived. Okay, so normally you have something like displaced jet. You have a particle that is long-lived, travels some distance, and decays into jets. Here, what you have pions. You can have many of them, because depending on how many flavors you have NF squared minus 1 pions. If you have 3 flavors, you have 8 kind of pions. And this makes that you don't have one single long-lived particle that decayed, but a multitude of them. You can have many, not 1, not 2, 8, 10, that decayed at different positions. Okay, and this jet is not coming from one single point. You cannot form a vertex. It's really a bunch of dark hadrons that travel some distance and then decay back to the standard model. This is why it's a very exciting, very peculiar signature. And here what you can see in this Fino paper is that there's a certain interplay with the normal searches and searches dedicated for this signature. So here you have a four-shed search that works very well when the stuff is mostly prompt. So 1 millimeter is not a huge displacement in terms of a collider. You also have the missing energy search, because if these guys are very, very, very long-lived and most of them decay outside of your detector, then it looks exactly like a missing energy search. And in between, this green curve is what the new search will win for you in terms of masses. And it's a lot if you move for this 400 JeV here, all the way up to 1.5 TeV in mass over here by doing this search. So CMS followed this paper here by Dan Stolarski and Andy Weiler from 2015. And they did again a very similar approach of doing some selection. There's criteria to tag, so to identify these emerging jets from normal jets that use displaced variables is quite involved, but at the end of the day, you can produce the very first result for emerging jets. This is slightly older, it's from 2018, but it's the only emerging jet result up to date from LHC. I know that Atlas and LHCb have it on store. This is being analyzed. But once again, this is just to show you how novel the new field is. Okay, let me see. And finally, there are these soups. These soups are very special because they go essentially to a regime that you're not used to. You have a very, very strong coupling, and the radiation there is spherically symmetric in the rest frame of the particle. So you produce something, if you look at the event display, I just stole this from a talk by MATHUSLA, you have activity all over the place. It's a sort of like a Christmas tree for your detector, but this activity tends to be very soft because what you are really doing here is splitting the energy of the collision into all these different energy deposits. Okay, so this is a gigantic nightmare, how to trigger, how to analyze, how to reconstruct. This goes very, very well deep into detector expertise. So it's not something that is at the reach of every experimentalist, but only people that is very well known and versed on the incredibly soft radiation can try to tackle this analysis. And this is why there's only a FINO paper and not an analysis yet on these signatures. Plus, besides that, it's essentially almost impossible to calculate because this is in the very, very strong regime. But it's a signature, it's a long-lived signature, and it's of the signature of these strongly interacting intersectors, and it's quite interesting. Okay, I reached to my conclusions, probably slightly off time, but let me try to summarize what I said. I hope that by the end of this talk, you will all sit back in your chair and say, well, LLPs are really theoretically well motivated. Many models have them. This is not a last resource of the theories that are just trying to sell their crappy theories, buy my book, but it's rather really serious models that have built in these long-lived particles, these mechanisms that produce long-lived particles, and that give you a very striking phenomenology, in particular the colliders. Now, current experiments, proposed detectors, future colliders, they cannot do LLPs, and they are all using them as an important physics case. Now, roughly speaking, there are three classes of signatures. You can have neutral long-lived particles. They could be fairly light because they would obey most constraints. They don't have standard model charges. That's what I mean by neutral. And these are mostly being targeted by the dedicated detectors. Of course, LHC people want to find them, but if they are just too long-lived, LHC will not see them. Or you can have particles, long-lived particles that are charged, the second category, under the standard model. And there you have all sorts of signatures, like the disappearing tracks that I was mentioning, or displaced leptons, or heavy stable charged particles, like the signature that I didn't go into details, but we use that in the freezing plot. And that come with its own challenges, its own merits, but since these particles are long-lived and charged, if they are produced in the LHC, we will see them because they will interact with the detectors. So this is a part where the dedicated detectors are not needed. And the last set of signatures is these strongly interacting intersectors or dark showers that, if you want, from a perspective, they are standard model neutral, but they give rise, or they can give rise to very peculiar signatures with these emerging jets or multiple displaced vertices that will not happen in a normal neutral LLP theory, where you maybe produce one or two long-lived particles. In the dark showers, due to this parton showering thing where you can start radiating dark gluon that split into a pair of dark quarks and so on, you can have more than two, more than three, more than four, multiple displaced vertices, multiple emerging jets, multiple semi-visible jets. So a collection of these signatures, like maybe you can have one semi-visible jet and one emerging jet, that are incredibly striking, and that they strongly depend whether the theory does look like QCD or not, that we don't know, and how these dark hadrons, what is the lifetime of these dark hadrons, which is also a parameter that at the moment we are treating as an unknown, because even if in a given model you could compute it, you need to do a very complex calculation, like a lattice calculation, just to look at the lifetime of the pion. So the phenomenological exploration, that is a very rich territory there to look, is essentially based on trying to make a very simple model with a dark pion mass, dark pion lifetime, roll along and see where this search takes you. And as I tried to point out, this is a very novel, very fertile territory, the dark showers. This is why I wanted to bring it up in this overview. And well, I hope you have all enjoyed it. And finally, a message that I stole from one of my colleagues. Thank you very much.
Thank you very much, Jose, for this very, very nice, very informative talk. So let me remind again that all YouTube viewers can ask questions through the live chat, and they will be passed immediately once I get them to Jose. So no questions yet. So let's see if there's any questions from the Zoom audience. So we open up for questions. Okay. Oh, Roberto, yeah, go ahead.
Yes, I have a question for Jose. Very nice the talk. I'm very, I mean, to see all the possible outcome that could be searched with the different search strategies. So I was wondering, because you mentioned that the only kind of Monte Carlo software program that is making an effort to try to get this signature is Pythia.
Mm-hmm.
So could you comment a little bit more? I mean, in the sense, because when people try to use Pythia to adapt to new signatures, it's kind of very hard to unreveal. So is it like an effort from Pythia within, or just
so
other people that start to tweak Pythia just for this purpose?
Okay, so let me tell you the bit more of a sociological component of this. So yes, as you said, Pythia is a Monte Carlo that requires that you essentially hard code the model. Okay, so it's maybe not the tool that you would first use for VSA. So what happened is that in 2011, 2012, there was either a master or a PhD student in Pythia. So these hidden valley models were out there, but the whole LLP thing that exploded much later. And the main head of Pythia at the moment, so Theorgon is Josh Strand, and probably mispronouncing it, took a student that said, hey, why don't you implement a hidden valley model in Pythia? Actually, the model is called hidden valley module, and then people say, oh, but this is dark showers. And then the student did that, and the student left the field. And then the whole LLP fever started. Yes, maybe fever wasn't the most happy example, but the whole effort started back, and then people look back at what tools they had, and there was this module that, I mean, just was there, nobody used it, and essentially allows you to do these kind of games of change the pion mass, change the lifetime. It has some limitations, of course. You cannot do everything. It has been actually recently updated in the context of SnowMass. There's a new version of Pythia that has like a newer dark, and there's a lot of people that is heavily involved into doing that. I understand that so it's not the Monte Carlo, but it's really the showering program. So Herwig and Sherp are the other main players in the game. So at the moment they haven't catched up. I imagine that they have plans. I mean, at some point they will become more or less apparent. Some people inside Herwig have certain plugins to run, but it's more sort of homebrewed stuff. So Pythia is the one that is available and robust. So the issue is not so much the Feynman diagram. I mean, you can do it in MathGraph, you can do it in Pythia itself, but the showering, right? Saying, I have here a particle with this PT. Okay, now I emit a dark gluon. Now this dark gluon goes to 2 dark quarks. Now this dark quark hadronizes into 2 dark pions and 1 dark kaon. Yes, this part is the part that is really hard. Yes, and essentially Pythia is only doing series that are SU and with, so there are certain limitations. But at the level of very rudimentary exploration that we are doing things is more than enough. I mean, it won't work if you say, oh, I want to do I don't know, let's E6 shower and connect it to string theory. It would be fantastic, but PTR doesn't do E6. It's just doing SUN. It wouldn't even do SON. Okay, so this is something that at the moment is working. Obviously, it's not that ideal to have only one tool that does a simulation because you also want to assess systematic effects. And the point between mostly PT and Herbig is that the way they approach the parton shower is conceptually different. They use different models to do this. The hadronization also is different. So it actually would be desirable to have it. It's not there. So, but it's, if you see, this is go back to that some point in 2011, 2012, so this was implemented and then it is sit there for some time and then now people is more actively using it.
But in principle, you could use MATGraph with a more complex model as long as everything would decay into dark quarks and gluons, such
but
that PTIA would do the shower.
You need PTIA for the shower. The real thing, the real problem is the shower. Yes, that's and MATGraph cannot do the shower. And you could, I mean,
but that's true also for standard model stuff, right?
Yeah. Exactly. Now, some people have, I think, for the soup thing, I think Matt Strasler has like a proto generator for soups, but that's his own very own thing, and I mean, it's not public or whatsoever. So there's still a lot of effort, or there's still a lot of room, not only for people doing BSM and so on, but also from people developing parton shower codes that could jump in, right? So it's call it an opportunity. I hope that at some point the competitors will try to catch up, develop their own products, and this competition will only be beneficial. But at the moment, I think we're all running PTIA 8.
Okay, thanks.
Great. Let's see. Nothing on YouTube yet. So let me ask one question now that we're on this topic. So okay, we have our SUN dark sector. So apart from most likely giving us a dark matter candidate, what other problems could such a sector solve? Have there works on how a dark sector could help with baryogenesis, or
so
I mean, what are the motivations for?
So there are. I didn't want to go into those details, but for instance, if you think of the framework of asymmetric dark matter, where people try to connect the baryon asymmetry with dark matter asymmetry, at least the setups that I know work in a strongly interacting dark sector. Right? So that would be one possible motivation for that. If you say, well, I'm going to take asymmetric dark matter seriously, fine. You need strongly interacting dark sector. Then there also works, for instance, that strongly interacting dark sectors could give you strong phase transitions in the early universe, and they could even source gravitational waves. There's a very nice paper by Pedro Schwaller on that topic, for instance, the PRL. So this is also another aspect of having a strongly interacting sector that you could connect to. And of course, gravitational waves are quite trendy, and only more data is only, I mean, doomed to come. So I think there's a very interesting connection on these kind of sectors with that. So I don't know much about the baryogenesis part because I'm not an expert, but since you can do asymmetric dark matter, I imagine you can also use them for that.
You can also do that.
I mean, this is not something new, right? People have used this kind of setups. Now, how this connects in terms of, I haven't seen much work in terms of making a proper link between, let's say, a dark shower search and putting a boundary baryogenesis model. Precisely because there are many model limitations. How will you compute? Okay, this is the lifetime and the mass. How do you translate it into a? I mean, it's not like in the Frisin paper that I was showing you where I have a way to. Let me go here. Yeah, I know like this line is dark matter mass of 12 keV, reheating temperature of 10 to the 10 Joule. I cannot do that in a dark shower model. I don't even know how to compute the lifetime of the dark pion given the SUN C and the SUNF. But certainly, if you only talk about motivation, these strongly interactive detectors can do much more, and I should have mentioned. Yes, so
Sure.
but at least right now the idea would be, I didn't talk about the relic, right? I said there's a dark sector. It might look like QCD because we know QCD, and then we roll along.
Yeah.
And within that, you have a palette of options that are essentially unexplored.
Exactly.
Very little, very limited. Results from CMS, that's it. But the revival, it's also very, we're talking 2015, and we have had, I don't know, I didn't mention this, but RPV-SUSY gives you lonely particles, but RPV-SUSY has been around for 30 years, probably, or more, right? Well, these dark showers is something fairly novel. So I hope it becomes a. I mean my own bias. I'm working on these topics. I think it has the potential to become an important topic, and also because it doesn't fall into the previously classification of one or two neutral lonely particles, one to charge. It's really a different phenomenon.
Yeah, it's a different, completely. And so speaking about that in the specifically about SUP that you were talking about triggering. So what's being discussed right now regarding how to trigger this kind of signatures?
Usual trick is set.
Sorry?
Usual trick is set. You have a set that decays to leptons, and then whatever comes with it goes to SUPs.
So you say that you generate it with an associated standard model particle, and that does a trigger.
That I think is a strategy, as far as I haven't looked in detail at the works, but that's a strategy. Because I don't think you have a way to say, I just got 1,000 hits of charge tracks of PT1 JEV in my detector. They are spherically symmetric. Can you please save this collision? No. It just won't happen. So it requires a different approach, essentially. And I think right now if you go back to the original paper of Strassler on hidden valleys, I think that's pretty much what they are doing. Because if it's fully hadronic and soft, the standard model is there with much more, with much higher rate, and there's not much you can do. But if you look at this paper of Simon, Simoni, Michele and Dean over here, the one where they actually call this the soft bomb. I guess the referee didn't like the term, so they moved to this funky acronym. They discuss how these things could be done. So it's not hopeless, but it's incredibly challenging.
I see.
And also, this puts you in a situation where you really need to understand a strong regime. So if you start reading some of these Strassler papers, there's even elements from string theory or sort of the ADS-CFT conjecture that could try to, if you really go to a very conformal regime of the SUPs, you could try to use some of these tools to make estimations. So it really goes to the frontier of calculability. This is hardcore QFT. I removed the hardcore QFT elements from my talk mostly, but it's quite hardcore.
I see. So any other questions? Nothing from the YouTube so far. We're very close to our time limit. So let me ask one final question regarding the comparison of dedicated detectors. Could you go back to this? Yeah, exactly. So there you have, right, distance from the interaction point, right? And you have the LLP mass range, but you have a bit of degeneracy over there, right? You have ANUBIS and Codex B sharing the same range. So what are the advantages of this kind? Like MATHUSLA is right in the border between being 10 and 100. So
it's a very complex world because all of these experiments are fighting to get recognition. And if they are actually proposed, I would argue that each of them has some peculiarity that make them worth it. So some issues are more of practical terms. For instance, millican, that is here, has essentially been recently integrated as a subdetector of CMS because it's using one of the CMS interaction points. So there's no need for approval. It's just moved to be a subcomponent of like the tracker. Now, MATHUSLA, Codex V, and ANUBIS, which are probably a very strong proposal. So the MATHUSLA, for instance, on MATHUSLA is, again, a football field on top of CERN. You can look at the display that I stole from Emma here. Okay, this is this huge thing over here. Okay, this is an aerial take. Now, this will be costly, of course. Will take a lot of money, and you say, oh, this is only doing LLPs or whatever. Now, the point is that if you look at MATHUSLA physics case and the different documents of MATHUSLA, there's also a program to do cosmic ray physics, because the area that they're covering is almost the size of Roger. Okay, so it also has a cosmic ray program that, since I'm not, here
the effective area, I guess.
I mean, if you sum up the number of detectors in Roger times the area, it's,
right.
That's what I mean, right? I mean, obviously the area covered by Roger is much larger in terms of distance, but the flag that you're capturing it's almost similar. Now I'm part of the MATHUSLA collaboration, but I'm not a cosmic ray physicist, so I cannot really say how strong the program is or so. But I'm saying, for those who know, the studies are there, how well you can measure this sort of shower depth, air depth, this X0, and there are many studies. So, for instance, and none of the other experiments, as far as I know, can do a cosmic ray physics program. Of course, you put that in the detector proposal and say, okay, this is something that we can do. Now, ANUBIS, for instance, ANUBIS is essentially, so if you want to go to the LHC, you need to take an elevator. But normally you only take that when you only use the elevator when you need to go down because something broke, so during the shutdowns and so on. So what the ANUBIS people said is, why don't we put the detector in this elevator that nobody will be using? Okay, so this is, if you want, this is the cheapest proposal in terms of just go there and drop a box and leave. Many of the proposals actually share this thing, but let me just tell you about this one, ANUBIS. Now, ANUBIS is getting criticism because other proposals shield themselves. MATHUSLA is shielded by the whole rock between the LHC and the surface. Codex V, which is something that will be put next to LHCb, is going to have additional shielding to remove kaons, pions, etc. that are produced but ANUBIS is not having any shielding, and they are making claims that they can do that. So the question is how effectively I think most of these experiments, when they get mature stage, they run sort of a prototype version. And right now, the point is to make in a convincing physics case that how they are going to operate. And since they are different, shielding, no shielding, there's the rock that shields you, or you need to put additional shielding and what not here and there, this changes what you can do. And also FASER is like MATHUSLA, but way smaller, but it's already approved. So also, if you were essentially competing with FASER, you cannot really do that. Now, for instance, as far as I understand, FASER doesn't have any tracking or whatsoever. And something that MATHUSLA has is five trackers layers with a space of 1 meter. So if you actually get an LLP that decays into BB bar, you will get many tracks. And if you decay the LLP that decays into a muon or a tau, you will get less tracks. So with MATHUSLA, you can do some more of, if you get a signal, you can do more identification, while in FASER, you essentially are doing a count. Yes, so I think FASER is not measuring energy. Neither MATHUSLA. I mean, it would be fantastic to have a full detector that can give you information. So it's a very complex game, and each of the detectors have pluses and cons. So this diagram is a good way to compare them. But again, each of them have its
has got its own subtleties. And
then the question is who will win? It's a combination of many different factors. And of course, you have to make the best physics case of all these things. And if you are running a demonstrator that show that this demonstrator is effectively working and your expectations were not wrong. That I think is the game. Now many detectors are actually operating: MAP, SND LHC, FASER. So, and in the next 1 or 2 years, all these other proposals should condense into whether they go forward or not. Now, this proposal I didn't discuss is the proposal to do a forward physics facility at CERN, where in this facility you will host many of these experiments. And this is something fairly new. It's in the context of SNOMAS. You can probably just look for it in Spires. FPF, forward physics facility, and there's a very large amount of documentation on why the physics case. So if you want to know, I haven't looked at that into detail, so I don't know what is the advantage of that versus other stuff that is forward, but for instance, MATHUSLA, CodeSB, and so on are transfers. They are really trying to look for particles with sort of heavier masses, more moderate APT, large PT. So this is something essentially going almost along the beam. And if you look at the SND LHC, I think they look also very forward, something like an eta of 8, which is almost an angle of 0. LHCb goes, ATA CMS goes from up to 2.5, CMS goes from 2 to 5, and then this SND LHC is in a different angle. So they serve different physics purposes as well. It's very hard decision, to be fair, and how to wait. Hopefully I don't have to do that. The more I can do is go in MATHUSLA, say MATHUSLA would be great to look for this and look into that.
Great. Okay, so we are already past the time, so I think it's a good moment to cut off the meeting. So thank you very much, Jose, for this very nice, very clear, very comprehensive webinar. And we'll be seeing everybody next on the 23rd of November, where we have Lina Nesim. So thank you very much for your attention, and we'll see you next time. Take care.